started. I would like to welcome you on a talk about microservices. Hopefully all of you must have heard about microservices. Is there anyone who haven't heard about microservice? Okay, so I'm in the right place with right people. But let me ask you a simple question. How many of you have developed your own microservices? Okay, so I hope after the end of this talk, when you will walk out this door, you will have enough knowledge to start and develop your own microservices. I would like to kick off this talk by addressing problems that are not only relevant to the big software giants, but problems that are also relevant to the medium-sized software house. And we will take a look on how monolithic and microservice architecture can handle those problems. Then we will take a look on some of the core concepts behind microservices that will help us to get started in order to build and write our own microservices. As you know, everything has plus and minus. So does the microservice architecture. And we will take a look on few of the pros and cons behind microservice architecture. And finally, we will take a look on how to squeeze all the theory that we discussed in this talk into a small demo application powered by Spring Cloud, Spring Boot, and Netflix OSS. A short info about me. I work for a company called For Finance IT. Also, I'm a consultant and architect basically around JVM and related technologies. Before we begin, I would like to mention that it is possible to build a beautiful monolithic applications. It's possible. Remember the word possible. But usually the monolithic application that we encounter in day-to-day life, they had a very beautiful vision, but the packaging when we reach the end of this application, it ends up with something like this. It's not written in any holy book that a monolithic should look like this, but typically what we encounter in day-to-day life looks something like this. I think if we make a light a bit dimmer, you will. Do you guys see everything properly here? Okay. Okay. One guy says so. So I don't know how to control. If someone can make the light off, it will be a bit better. Better? Okay. Okay, so let's take a look on what are the common problems. Complexity. Complexity can come in many flavors. It can come due to new user stories, business expectations, business needs. You need a competitive advantage. You need to integrate some, business intelligence solution. You name it. But complexity is not this nice person who comes to your door and say, hey, could you please let me in? It comes to you, it smashes your door in two halves, and if you are hiding yourself under the pillow, it will find you. If you try to hide yourself under the bed, it will still find you. So the point that I'm trying to make is that we as a developers have to address the complexity. In monolithic application, this complexity hits you directly on the face, due to which it's hard to board new developers or even move existing programmers and increase productivity at the same time. A new developer have to install a whole set of tools, libraries, application server, database, have to go through a big README file, and then this README file is outdated, and then he have to Google it, find something on Stack Overflow, then tweak it for his own operating system, and goes not what. And remember, at the end of the day, his task was only to add a new button in the GUI. I mean, just think, it's insane. And we call ourselves, at the end of the day, we are engineers. In microservice architecture, this complexity is not disappearing. This complexity is moved to another layer, more precisely the interaction layer or distributed system. In order to support new user needs and expectation, we need to upgrade our legacy components. Well, first of all, upgrading monolithic application is no fun, and second of all, due to layered architecture and long-term commitment to tech stack, it becomes really hard to upgrade few parts of the legacy system. Whereas in microservice architecture, it's perfectly possible to replace old microservice with a new one as long as the new microservice fulfill its SLA and don't break its API. Workaround. Since monolithic application require long-term commitment to a tech stack, usually we don't have options to kind of upgrade part of application just to add a new tech stack. It's possible, but due to time pressure and business needs, it's not so easy to convince the board members. So usually the programmers are left to do a lot of work around. They want to add new features to their tech stack in order to make their life easier. Because they cannot remove this full tech stack and throw it, because it costs money and time to rebuild the full monolithic application. In microservice architecture, it's perfectly possible that we can choose the best tools available to build a particular microservice. I'm not saying that each and every microservice should be built using a different technology set. What I'm saying is, if there is a need to fulfill and deliver a particular business case, we have the leisure to choose the appropriate tech stack and avoid workaround. When we speak about monolithic application, we are speaking about multiple responsibilities. And hence, when a new functionality pops up, it's quite hard to figure out where it belongs to. Whereas in microservice architecture, when we speak about microservices, we speak about SRP, single responsibility principle. Hence, it's easier to figure out where this functionality belongs to. In monolithic application, it's easy to maintain standards because we have one application, so it's quite easy to maintain the standards, but on the other hand side, it's hard to maintain the quality. That is, it's easy to mix the good and the ugly parts of the code together. On the contrary, in microservices, each team, we have small teams, and each team is responsible from the beginning till the end for a particular microservice, so it's easy to maintain quality. Whereas it's hard to maintain standards because we have large number of those small teams, so it's hard to maintain standards. It's not impossible to maintain standard, but it requires work to maintain and coordinate those teams. Refactoring, I think this is something which all of us love to do. I mean, throw as much code as possible and then go home. And still the application should work. But usually when we try to refactor a big monolithic application, we start with something like this. And we end up something like this. Although unintentionally, it happens, but it happens. Why? Because everything is glued together so tightly that we have to touch those parts of the application that even we didn't intend it to touch during our initial refactoring. In microservice, when we want to refactor a particular microservice, we don't have to think about the full system. We even don't have to bother about how the full distributed system works. We are only confined to our domain of refactoring. As long as we are not going to break our API and SLA, service level agreement, we are good to go. So now we know some of the common problems. Let's take a look what microservices are. Well, it is a way to create application in which the full application consists of small components, and each component have a single responsibility. When we read about the word microservice, I remember the word micro from physics from back in the school. It is clearly defined. 10 to the power minus 6 is micro. If you go minus 3, it becomes different, and if you go minus 9, it becomes nano. It is clearly defined. But in our domain, microservice is something small, and small to me can be different to you. So some people tend to kind of have this idea that microservice means that a code should be like X numbers of line, that it will be 100 lines of code and it is a microservice. No, it's not. Some people think it depends also on the number of methods. If you have too many methods, it's not a microservice. Well, when you are thinking about micro, think about the responsibility of every component. That's what micro implies here. It's hard to measure. It's not like that you can say, okay, this is micro. When you are building a microservice, you are thinking that each and every component should have one responsibility, and it should do that thing and that thing good. So it's like an extension of SRP principle, single responsibility principle. And each component, as I say, talk to each other via language agnostic API. So we don't assume that one component is written in Java, so others should also be written in Java. So let's take a look on some of the core concepts behind microservices. First is service registry. How many of you have heard about service registry? Okay, so let me recall for all of you what service registry is. So let's imagine you have two services, service A and service B. And service A want to communicate with service B, but let's assume that it is a vanilla communication. So we don't have a load balancer and proxy and stuff like this. So what service A need to communicate to service B? It needs its IP address and the port on which the service B is running. And then it can communicate with service B. But let's now imagine that these service A and service B are microservices. So as long as we step into the microservice world, our dreams are shattered. Our assumptions are broken. Why so? Well, one of the key strengths of microservice architecture is scale on demand. We can scale each and every microservice when and as it is required. In order to support this functionality, we usually end up deploying our services on an infrastructure where nothing is guaranteed. And this nothing means that, for example, when you run your service, there is no guarantee that it will be running on the same port. You may ask a question, how? Well, for instance, cloud. In cloud, you don't have a guarantee that next time when you launch your service, it will be running on the same port, or even on the same IP. The cloud provider can choose a dynamic IP and assign to you. So we need a single source of truth, a place where we can go and ask questions like, hey, do you know on which port service B is running? Or what is the URL of service B? And when service B comes into action, it can register, detect that service B is alive. And when service B is dead, it will just remove it. So we need a single point of truth where we can go and ask those questions. And this is called service registry. There are 3 flavors of service registry, but there are more. I mean, I have listed only 3 of them, but there are more than 3. But just for the sake of this presentation, let's focus on these 3. So if you are, which of them you should use when you started to develop your own microservice? You should use this one or the middle one or the third one, or you like the logo of Zookeeper more than Netflix. Again, the answer depends on how you are going to deploy your services. So let's say if you are going to deploy on an infrastructure where, for example, consistency and partitioning is important for you, so you don't really care about the availability factor, then Zookeeper is good enough. So in such a scenario, you don't really care about network partitioning, zone-based partitioning, usually like your private data center, in which those events can happen but are very rare to happen. And Zookeeper is consistent and partition. But let's suppose that you are now want to deploy your services on an infrastructure where consistency becomes less important. So where the events like zone-based partitioning or network partitioning is more likely to happen. Then you can choose Eureka. It is created by Netflix. It is open source, and it is, like many of their components, is battle tested. Consul is the one which I like the most, but for the sake of this presentation, I will concentrate on Eureka, but it is also targets the cloud quite nicely, and it's also available and partition. So what are the components of Eureka? Well, Eureka is a service registry, as I said, but it consists of 2 parts, the server and a client. How the communication between a client and a server looks like, because this is important in order to understand Eureka. So we have a client. So the first thing that client should do is he should register, and he does it by sending an initial heartbeat after 30 seconds. Once the client is registered, then he have to renew the lease. And renewing lease means that he have to inform to the server after every definite interval of time that he is alive. And he does it by sending a constant heartbeat after every 30 seconds. What happens if server don't receive these heartbeats? Well, server wait for about 90 seconds, and if still there is no heartbeat, he assumes that the client is dead, and he just removes the client. But let's assume our client is registered and is healthy, is sending the heartbeat after every regular intervals. The next step which he have to do is fetch some information from the server. He does it by fetching the registry. Registry is the information that helps it to locate the other services. And remember, it not only retrieve this information, but cache it. And as you all know, that once we are caching an information, the cache becomes stale. So we have to update the cache periodically. And the client does it by asking for update after every 30 seconds. In every 30-second update, it don't ask for the all information, like again and again and again and again. It just asks for the delta, and delta means the difference between the last fetch cycle and the current one. So it is very tiny information. Lastly, when the client wants to shut down, he sends the cancel request on shutdown, and the Eureka removes the client from the registry. Are there any questions till yet? Okay. So the second concept is about load balancing. I mean, why should we really care about load balancing? Well, as I said, that a client microservice can have n number of instances up and running. So let's say a client say, I want to communicate with the service B. And the server say, OK, you have 10 instances to talk to. So which one of them he should use? The first one, the last one, the middle one? I mean, those questions really matter in the distributed world. And in order to answer those questions, we need a client-side load balancer. Fortunately, Netflix have open source one such component for us called Ribbon. It's a client-side load balancer. It provides lots of cool features like, for example, zone affinity. When you have this feature enabled, then the load balancer knows, for example, that, OK, out of 10 services located in 4 zones, let's say 2 zones are down. They are dead completely. So he's never going to route a traffic to that dead zone. So, and it have these features built in. It have also a high built-in capability to handle failures. How it does so. So for example, when you have the list of servers, then it can dynamically determine which of them are alive and which of them are not alive. Hence, it can avoid, for example, to route the traffic to those servers that are no longer ready to handle the request. And lastly, it uses rule-based load balancing. So we can, by default, it uses round robin, but we can easily plug our own rules. Okay, the third concept is edge service. So I think till now you agree that it is not a very clever approach to expose directly the address of a microservice to the client, because this info can change dynamically. But let's imagine that you want, for example, to enable authentication. So all the calls made to your API, you want to authenticate. Or for example, you want to enable the dynamic routing of the request. In order to handle such a scenario, we have something called edge service or gateway. And basically, Netflix have provided us with Zool. What Zool is, it's like a proxy. It consists of 3 parts: pre-routing, post. So when if something goes wrong in this stage, it falls back to the error stage. In order to understand Zool, let's imagine how the request flow through the Zool. So when a user make a HTTP request, it goes through a pre-stage. And in pre-stage, you can do all sort of things like, for example, authentication. You can authenticate a request. And you can write your own filters to do the pre-checkup. Once the pre-stage is finished, the request is forwarded to the routing stage. In routing stage, we can determine where to route the request. We can, for example, also use some custom-based logic, like whether we should use dynamic routing or not. So all the stuff related with the routing we can do here. Once the request is routed and the response is back, the request is handled by the post stage. And in post stage, you can do actions like adding default HTTP headers to a request. Or you can, for example, expose data like matrix data, which can be consumed by Grafana in order to make nice graphs. I will show you at the end of this presentation metrics from our production system. And finally, the response is handled back to the client. So this is how the request goes through a Zool. We have a request, it goes to the pre-stage, routing, post. If anything goes wrong, we fall back to the error. If nothing goes wrong, the response is sent back to the client. But are there any features of that Zool, I mean, apart from these simple filters, we can obviously create our own HTTP servlet, extend it, and write some simple code. Why do we need Zool? Are there any more feature which it can provide? So first of them is load shedding. In a simple plain English, it's like we can allocate the capacity for requests. And if some request goes over that capacity, then Zool, we can configure Zool to start dropping those requests. Also, if we want to enable OAuth authentication, and in order to pass those tokens across the microservices, Zool can handle those pretty well. Sometimes we have a need that we don't really want to forward the request to the cluster of microservices. Sometimes we just want to return the response directly from the edge service. In this case, we can use static response handling feature of the Zool. This is the feature, surgical debug filter, which I like the most in Zool. Let's imagine you have your production up and running, and one client, only this client, have problem accessing your system. In order to debug the production, what you can do, you can extend the surgical debug filter, and then only the requests that are coming from that particular client, you will be able to intercept and see what's going on. The things becomes quite interesting when you can use the same concept to debug not only a particular client, but also, let's say you have a cluster located in the east zone and the west zone. And for some reason, east zone is working slow or it's experiencing some problem. You can use the same concept of surgical debug filter. You will intercept the live request and then see what's going on. The last feature is stress testing. So thanks to this feature, what we can do, let's say our team have built the new release and we are ready to deploy. But we can configure the Zool that it can, instead of enabling 100% of the traffic and blowing our build because it's a new build, we can configure Zool to increase the traffic slowly and gradually. So we can increase like 5%, then 10%, and we can record all the time how our build is performing. And if we, for example, see that after 75% of the traffic, our build was good enough, but let's say we increased the traffic up to 80% and the build started to return the response slowly, or we started to experiencing some problem, we can report to the team. So as you can see, we can do quite a lot with Zool. It's not like simple HTTP filters that just intercept the request and delegate the response. The last concept, which is quite important before we start building microservices, is failure management. In distributed world, we have hundreds of moving parts. And as you know, when we have hundreds of moving parts, it means 101 things can go wrong. And when you are building distributed system, you are responsible for failures. And you are also responsible to handle the failures, to not let other failures impact your build. And Hystrix is the one that supports failure management. It can support failure management like latency, failure originating from fault, like service is dead or service is taking too long to reply. It also uses the fail fast approach. So rather than waiting for the disaster to happen, it uses pattern like circuit breaker. I will show you in a demo how it looks like. So I think these are the 4 concepts that first we discussed in theory, and now let's very fast take a look on pros and cons of microservices. So when it comes to the pros, it's quite easy because we have component-based approach, as we can really excel at single responsibility principle. We are not confined to a particular tech stack. We can scale, and really we can scale at magnitude of our needs. And resilience, which means if one part of my application fail, not full build have to go down, full production have to blow. But the price, on the other hand side, for all those features is, first of all, in monolithic, we had a one big application. So one piece is easy to manage. And now we have hundreds of small pieces, running wild in the production. The second is arsenal of tools. I mean, when we started doing microservices, it's not like we need one tool or two tools. We really need lots and lots and lots of tools. So it put a lot of pressure on DevOps culture. So if your company doesn't like DevOps culture or stuff like this, I think it's hard to embrace microservices. Testing and transactions are something that we take very easy or granted when we are dealing with monolithic applications. But in microservices, those things require to rethink how we are designing our systems. So things like eventual consistency versus ACID compliant becomes quite important. So here is a demo application. It is backed by Spring Cloud. I'm not going to explain what Spring Cloud is because I think one tweet from Phil Webb have nailed it down. So we can use either Spring Framework or we can use Spring Boot, but the Spring Cloud is something that is uses all the goodies like nice principle or encapsulating Netflix stack in some annotation and stuff like this. So Spring Cloud, we are going to use Spring Cloud because it is possible to use Netflix without even Spring. We can just use and create old school, new object and stuff like this. But we are going to use Spring Cloud because it is cloud ready and most of the stuff is done by Netflix Spring guys to help us to use Netflix components. The demo application is going to look something like this, that we have a catalog service which is going to talk to product, price, and comment service in order to build a catalog. A user requests a catalog and he get in response a catalog. Okay, so I have only one screen here, so let's go. File. Okay. So the first component which we need is Eureka server. I mean, do you remember the client and the server from the slides, few of the slides before? So the first thing we need a Eureka server that can listen for the client to register. All we need in Spring Cloud is to annotate our Spring Boot application with @enable Eureka server. And what it is going to do for us is it is going to create a Eureka server with default settings and will fire it on the port 8761. Obviously, you can override the defaults by creating an application.yml file. Okay, so once we have a Eureka server up and running, we can now concentrate on creating some microservices. So let's first try to create a microservice that don't need to communicate with external systems. By external systems, I mean it don't need to issue HTTP requests to fetch some data. Comment service serves a very good example for such a condition. So as you can see, this is another Spring Boot application, but this time I have annotated it with @enable discovery client. And all this annotation is going to do is going to help the Eureka server to register my client, in this case, this microservice. And that's it. Our client and server communication is all set and done. The next thing that we need in order to, now we can concentrate, for example, on our business logic. And in this case, I have a comment service. It's a REST controller, nothing fancy here, which listen for the request mapping of comment. Just to make things simple, I have only one method here, find comments. And what this comment method does is, for given product ID, it simulate product comments generation. And that's it. But in real life, feel free to have there as many methods as possible. But for the demo purpose, I have added only one method. In the similar manner, I have price and product service. So just to show you, I have nothing under my sleeves, and I have no sleeves. I am going to show you here very fast that this price service looks the same. I have enabled discovery client, so it will help to register with the Eureka. And then I have my business case here, in which I just simulate generating price. But now let's try to draw our attention on a service that needs to communicate with external systems. And in our case, It can be, third-party system, or it can be bunch of microservices. You will notice that this and this annotation makes sense, but why we have @enable histories? Well, when we are going to talk with other services, those services can be down. I mean, there is no guarantee that those services will be up and running or they will reply instantly. So in order to handle the failures, so basically, rather than blowing your build and telling to your boss that, oh, this third-party API was down, and that's why I woke up 2 in the night, you use histories. And now let's take a look how this business logic will look like. So I have a method called find catalog, which for a given product ID creates a catalog. And as you can see, a catalog is nothing but a POJO. There is nothing fancy going on here. But what we does is we fetch the product, the comments, and the price. So in order to fetch the products, I need a REST template. Does all of you know how the REST template works in Spring? Or how many of you have used REST template? Okay, so in one sentence, when you want to make a REST call to another API or another resource on the internet, the Spring have provided the REST template. But since we are building microservices and we are in cloud, and you remember about this client-side load balancer ribbon, all what I need is I can say @load balanced, and Spring is going to inject the REST template for us that have all baked in support for ribbon. And now I'm feel free to program my logic. So when I fetch the product, I say, okay, get this object from this URL, and we will take a look how this URL is resolved. And if something goes wrong, then just go and use this method. And as you see, every logic is executed as @histories command. Because remember, if you enable the histories, it is not enough that everything is magically safe for you. You have to use particular method to annotate how you should handle the failures, because it's up to the developer to see whether it makes sense, for example, to return a demo product or maybe return something else. So that's why this full method is executed as a histories command, and I say if something goes wrong, just use the fallback. In the similar manner, I have a histories command and a price fallback. And when I have a comments, in case of failure, I return the empty array. Okay, so now I will show you how this communication looks like. So first of all, I can fetch the information from service registry. And as you see, this is some bunch of JSON. And I think all of you agree that except of taking some space on the screen, it doesn't make so much sense. So let's take a look on here, sorry. We can, for example, parse this JSON to extract some relevant bits of the information. And now you can see that service registry gives you all the information, like on which port, what is the IP address, what is the host name, and what is the service name. You are not only restricted to use HTTP, curl client. You can use, Spring Boot have provided a nice GUI where the same info is represented here. And as I said, it is running on localhost 8761. Localhost because I don't trust Wi-Fi during presentations, so that's why it's localhost. But now let's try to make a request to see something more interesting. So I make a request to the product service, to the catalog service, and I get a catalog here. Okay, but what, for example, Okay, but, and it will be tricky here because I have very bad resolution here, but let's see. Okay, I make another request here, and you see that we have a histories, and we have here, and we can sort it alphabetically. Okay, so we have one request we made, and circuit is closed. It means everything is okay. But let's try to do something more realistic. Realistic in a sense that let's try to, for example, kill the comment service right now. So what do you think will happen to my application? Does my full application is going to blow, or magically some part of the application will survive? Come on, guys. Okay. Okay. So just to show you, I have killed my comment service. And in this case, you can see that I have empty array of comments. Why? Because in my code, I instructed that if something goes wrong with comment service, use this fallback method. Okay, but interesting enough, if I now, let's say I want to issue some request here. Oh, and you see what started to happen here is the circuit becomes open. So I made 100 requests, out of which 41, okay, let's make it once again. So I'm making 100 requests, and you can see that Hystrix have only allowed one request to go and check whether the comment service is alive. In 99 requests, it just did short circuit. And short circuit means that it is even not going to bother to invoke the comment service. It is going to use the fallback method and going to return the response. Why it allowed only one request? Well, it can be configured by you, how many requests you want to allow. Because from time to time, it is possible that maybe the comment service came back to the life and everything is working properly. So if I, for example, increase the tendency to now, let's say, 10,000 requests, if I will not be handling those errors, right now my full application will blow up. Why? Because look, I have only 10 threads here, only 10 threads. And as you know, whenever a request comes, the Tomcat create a new threads and wait for the service to reply. But in this case, you can see the performance of my application is not getting impacted. I can see here that I have my fetch comment, which is now 100% down, and I have price service and product service, which are up. What is the benefit of this approach? Again, it not only helps to show you this nice dashboard and stuff like this. There are some nice patterns like circuit breaker and some best practices that are described by guys how to handle errors in a distributed world. And Hystrix is the end result of this. So it is the child of these parents who are really nice and who are going who want to do everything in a nice and proper way. Okay, but that's nice, and it's still going on. Let it go on. I can run the same application in the Docker. So how many of you don't know Docker? Okay. Well, Docker is a container-based approach. So right now I'm running this this application via IntelliJ. You can run by console. But let's say when you are deploying on the cloud, then stuff like, if I try to relaunch this same application 2 or 3 times, I will get that the port is already in use and stuff like this. Docker is a container-based deployment. Container-based deployment means that each and every service gets its own infrastructure in terms of file system to run the microservices. And the beauty of this is that you can scale on demand. And many times we heard this excuse that it works on my machine, it works on test, it works on pre-built server, but it does not work on production. So Docker is your answer to this, this type of problems. Okay, I can, in order to use the same application with Docker, I can use Docker. Oops. Wait a minute. Okay, here I am. Okay. So here I am. So I can create Docker images I can create Docker images simply by using a Gradle plugin, and it package my application into a image, and Docker use those images to run my application. I can, for example, list you the processes. So the same applications which I run from IntelliJ are running via Docker, and it's quite simple. If you want to map your file, all you need is you can create a docker compose.yml file, and here what I say, okay, this can be foo bar, anything. I mean, it is not relevant. The image is the one that I created, and this name comes from my Gradle file. You can check the demo application hosted on GitHub for the details. And as you can see, I can pass the Spring environment. In this case, I created the beans that I want to be activated when the profile in the Spring is set to Docker. And here I'm saying, okay, I want to map this port on my machine to the container port. But the interesting thing is here, for example, look, the product service, the common service, and the catalog service. They all can run on the port 8090. I don't have to no longer think about port conflicts or an environment where these services will not be running. So in order to make things a bit interesting, I have did here Control R. I have did here. Okay, let's curl. Okay, so I'm running something on the Docker on the port 8766. And I have added there thread.sleep there. So my services are going to sleep there. But as you see, it took some time, but I get the response. Well, in the distributed world, how do you find that how much time each and every part of the distributed system is taking? Well, we can use something like Zipkin in order to do. And Spring Cloud Sleuth provides us, it wraps the Zipkin library for us. How many of you know or heard about Zipkin? Okay, so it is an open source. So Zipkin is a library based on a paper from Google. It is an open source created by Twitter, but the paper on which it is based comes from Google. What it does is, in a nutshell, it allows you to trace your request, how it flows. So for example, when I make a request here, I can see that, okay, the first request that I made here went to the Zool, then the catalog, and then the Zool. So this is the high-level overview. But okay, the catalog service also had something to do with product service. So here I can click, and I can see what happens inside the catalog service here. And I can see the full duration here, how much time it took to process. And here I can see the individual bits of the request. So I can zoom in here and see, okay, and see how much time each and every of those requests took in order to process the response. It comes handy when you are deploying anything on the production environment. Why? Because it allows you to trace everything. Everything means each and every call going from one microservice to another microservice to the third, so on and so forth. And I think that's all from the demo. So now I will show you, let's back to here. Okay, play. So this was a demo application, but microservices in real life or more closely in production does not look only about the 4 tools. There are a whole lot of tools that you have to use. Grafana for monitoring. We have touched only few of them in this presentation because of the time. But if you are going to do it in the real world, you have to think about all those tools. Because as I said, it hits really hard on infrastructure. If you want to do microservices and you don't want to care about like distributed tracing or how the system behaves in time, so this is the matrix. I have changed the label here. But what this matrix represent here is that when, for example, do you guys see the green arrows, those tiny ones. So those are the arrows that we used. So whenever we are deploying a new version on a production, we tell to Grafana that, okay, mark that with an arrow. And then we have the performance there, here. Here we have the number of the thread states. So because we can have large number of threads used in distributed systems, it's important to know how the thread pool is behaving with time. We can have DB connection, but the thing that is quite relevant for the business perspective is also illustrated here, order process. So this is a matrix that we generate like after every 15 minutes. We gather the data and we plot it on Grafana. And what it does, it gives us idea like how many transactions were processed in per minute or in per second, or how many of them were above $20,000 dollars or euro, whatever. So when you want to expose such an info, you can do it easily also in microservices world. But this part is not necessary, but it's quite useful when you are building your applications, and at the end of the day, your boss is paying you not to come to the work and stare at the screen, but to generate some revenue. So I think that's all from my side. If you have any questions, here I am to ask. Thank you.